So welcome to the third video of this course on quantum processing. Last time I mentioned the qubits and how we can formally write down qubits in terms of superposition state. We also mentioned the tensor product state and finally concluded with the measurements. So today I will talk about operations. So operations in quantum mechanics are very important to map state into another state. And the first exposure of operations here are the unitary operations, the unitary transformation. So if I have a phi, and this phi is a kind of superposition 0 and 1, I transform it by some unitary transformation. I map it into another state. I get it into another wave function. So what I will talk here about is just the rotation matrix, the rotation operation, and also the Hadamard, the Pauli, and finally I will conclude with a block representation of a qubit. So why we are interested in unitary transformation? The unitary transformation has very important, two important characteristics. Here, if I take the final wave function, I overlap it with itself again, I find that I take the wave function, here is u applied on, so just take the conjugate of this, is the bra with the unitary conjugate, and I overlap it with itself again, I find it's equivalent to 1. So unitary operation here preserves the inner product, preserves the orthonormality condition for the wave function. And also I take the unitary operation, or the unitary operator, and with its conjugate it's equivalent to nothing else than the unitary matrix. So it preserves what we call the length of the state. Okay. The first example of this kind of operation is the rotation operation. Rotation operation can be written like this. You have the diagonal, 2 cosines, and the off diagonals, 1 sine and 1 minus sine. If you take the conjugate of this of this matrix, it's actually equivalent to its conjugate of itself. So actually just getting that for minus theta. So if you just kind of check it mathematically and write down some sort of transpose, you can see that the rotation matrix of minus theta is equivalent to the transpose of this rotation itself with theta. And also if I can multiply our theta with our minus theta, just substituting with minus theta, you can find that it's equivalent to writing the rotation matrix here multiplied by its conjugate, by its transpose, conjugate transpose. And both are equivalent to unitary identity here. So this kind of, we're making sure that this unitary transformation. What's unitary transformation here for rotation? If I have a 0 and I rotate it around a theta, so I just flip it in the other direction, or maybe I transform all the system, all the superposition system into another kind of rotation in the Hilbert space. So you can check it by yourself and see what I said for unitary here, for unity character. So let's take an example. So the example here that I apply the rotation operator over the plus, or over over the 0, or maybe over the plus, whatever you like. Here I mentioned 2 examples for 0 and minus. So you can get here, multiply, you will find that it's equivalent to cosine theta with, actually this is the state 0. And also with sine theta, and this is the state 1. So wow, so you transform, if you take an operator over the 0, it's equivalent to superposition here for cosine and minus and sine, and for 0 and 1. The same operation, if I apply it on minus sine, I can take this, I can get this value. And this value of matrix, you can maybe get it more interesting like this, which is cosine theta of 1 and 0 plus sine theta for 0 and 1. That's right. Also plus sine theta for 1 and 0, and plus maybe minus cosine theta for 0 and 1. Here the same, you have 0, here the same, you have 1, and here for sine you have 1, and here is for you have this 0 and this 1. Here we have the 2 0 plus 1 is the 0 plus 1 is for sort of kind of transforming into different bases here. So the rotation is interesting, but let's take another look at another operator, and it's the Hadamard operator. What I said for Hadamard operator. So the Hadamard operator here, it's the kind of matrix. This is 1 over square root 2, and this is 1, 1, and this is 1 minus 1. If you look at, I apply just simple multiplication of matrices here. So matrix multiplied by the 0, or maybe this is 1, so you get 1 minus 1. So expand it, you will find that this is actually a minus sign, right? What about the 0? I applied on 0. So this this Hadamard operator over the 0 will lead me, check it, that, think for yourself here, you find that this is the plus sign. And this is what we call the Hadamard basis. So the Hadamard transforms zeros and ones into this plus and minuses respectively. So another operation here is the Pauli operation. So you can look at the Pauli operation for Pauli-Spain matrices. We already know a lot about them from quantum mechanics. So this is for x, z, and y. So let's apply kind of operation over the 0 here. So let's apply x, for example, on 0. You multiply them and you find it's equivalent to 1. And for y operation over 0, you can find it's equivalent to minus I 1. What about the z? You find the z, multiply, and you can find it's equivalent to 0. So you can see that I transformed 0 to 1. This is what I call bit flip. So very nice operations and very nice characteristics for our Pauli matrices here, that if I apply x over a bit, it can make a flip operation, like not gate, for example. Like what happened exactly when I did it for x. So over 0, you find it's equivalent to 1. It's what I call bit flipping. So what about z? So the z, if I can see what I did for z, that the z operations over the vector for 0, it gives me 0. But it can actually give me 1. If I apply z over 1, I can get 1 in addition to minus. This minus sign did not appear for the 0, but appeared for 1. So this is what I called the phase flipping. This is what I call the phase flipping. So what about if I make kind of operation for the plus and minus? Let's see another characteristics for z acting as a flip operator at the 1 and also bit flip operator on 0. But what if it's applied on the plus sign? You find that as z applied on plus gives me kind of minus. So this is what I call the bit flip again. So from here we can conclude that z can act as both bit flipping and also phase flipping. Bit flipping for the Hadamard basis for plus and minus, okay? But it can act as a phase flipping or phase flipper for only the 1. But for 0, it does nothing. So it's one of the intriguing characteristic for z operation or Pauli z matrix. What about y? Y can combine both, actually. If you apply y on 1, it can act as applying, because actually y is nothing else than operation for z over the bit and another x, so you can transform what got from z into x, and x transforms it again. So you can take an example here, y operation on 1, and you can take it one by one and see that it's equivalent to minus. So there is a flip by the z and also another flip for bit flipping.